Welcome to the deep dive. We take complex ideas, break them down, and hopefully give you those aha moments without the usual overload. Today, we're getting into something really interesting in AI, how we make large language models, LLMs, actually better at reasoning. We've got some compelling research here on a new method called Archer. Our plan is to unpack what it is, how it works, and why it's causing a bit of a stir.
It's definitely a critical area. As these LLMs get more powerful, improving how they reason, how they reflect and plan, that's key. The typical ways we've tried to train them using reinforcement learning often just, well, treat all the output the same. This research on dual token constraints for RLVR, it offers a smarter way. It helps distinguish between the facts an LLM knows and the logical steps it uses.
Okay, so Archer helps LLMs learn better by understanding that not all words or tokens in their output are, well, created equal. It sounds like a more nuanced way to get to a more capable LLM, which is super relevant if you're following AI developments.
Let's maybe start with the challenge itself. So LLMs learn a huge amount of world knowledge from their initial training, right? Supervised pre-training. But to really boost their reasoning skills, thinking, planning, we need these post-training methods. And reinforcement learning with verifiable rewards, RLVR, is a big one.
Right, RLVR. That helps them get better at reasoning.
Yeah.
But you're saying the older approaches had a kind of blind spot.
The earlier RLVR methods basically applied the same training signal to every single token in the LLM's response. The issue is different tokens do different jobs. You've got low-entropy knowledge tokens. These are like facts, specific terms, pretty predictable. Then you have high-entropy reasoning-related tokens. These are more like the logical glue, the connectors, the words that guide the step-by-step thinking.
Ah, okay. So treating them the same is like telling a builder to use the same technique for laying bricks as for designing the whole building blueprint. Different tasks need different approaches.
That's a good way to put it. Some methods did try to separate them, using things like gradient masking, just blocking updates to certain parts, or asynchronous updates, where different parts learn at different speeds. But this research points out a pretty big flaw. Doing that can actually break the connections, the semantic links, within the output. If you stop the knowledge tokens from learning entirely or train them separately, it can mess up how the reasoning tokens learn because they're all tied together.
Okay, so that really sets the stage. Those earlier methods had drawbacks. How does Archer come in and, well, fix this? How does it handle differentiated learning without breaking those links?
Archer takes what they call an entropy-aware RLVR approach. It uses dual token constraints, but crucially with synchronous updates. What that means is it updates all the tokens together at the same time, but it applies different levels of training pressure depending on the token type.
So it's not separating them physically, but giving them customized instructions simultaneously. A tailored learning plan for each type, all happening at once.
That's the key idea. First, Archer figures out which token is which. It uses something called response-level entropy statistics. High-entropy tokens usually signal those logical jumps, the reasoning bits. Low-entropy tokens tend to be the factual stuff or just completing a sentence structure. And doing this at the response level is important because, whether a token is high or low entropy can change depending on the question asked or even where it appears in the answer.
That makes sense. A fixed threshold wouldn't work well if some answers are just generally simpler, right? It's about the context of that specific response.
Yes. So once it knows the token types, Archer applies two different constraints during that synchronous training. First is a clipping constraint. For the reasoning tokens, the high-entropy ones, it uses a higher clipping threshold. This basically encourages more exploration, lets the model try new ways of reasoning, but for the knowledge tokens, the low-entropy ones, it uses a lower threshold. This helps lock in the factual accuracy, stops the model from forgetting things it already knows. And the second constraint is KL regularization. Think of this like a penalty for changing too much from the original model. For reasoning tokens, it applies a weaker KL penalty, a smaller weight. This gives them more freedom to adapt and learn better reasoning paths. For knowledge tokens, it applies a stronger KL penalty, a bigger weight. This keeps them tightly bound to the original factual knowledge and helps prevent what's called model collapse, where the output just degrades.
That sounds like a really well thought out system, balancing exploration for reasoning with stability for facts. Okay, theory is one thing. How did it actually perform? Did Archer make these LLMs measurably better at, say, math or coding?
The results they reported are quite strong. They tested Archer on some pretty tough math reasoning and code generation benchmarks, and it significantly beat the previous RLVR methods.
Can you give us a feel for the numbers? How much better?
Sure. Compared to a baseline RLVR method called DAPO, Archer showed, for instance, a plus 6.6 pass at 1 improvement on a math benchmark called AME 24 and plus 5.2 on AME 25. For coding, it was plus 3.4 on Live Code Bench version 5. And maybe more importantly, when they compared it to other leading 1.5 billion parameter models designed for reasoning, like DeepScaler or Nematron, Archer came out on top with the highest average accuracy on both math and coding tasks.
That's quite significant, especially hitting the top spot against comparable models. What about the training itself? Was it like faster or cheaper to train?
That's a really interesting point they make. Archer didn't just perform better, it did so much more efficiently. It achieved these results with just single-stage training. For example, the ArcherMath 1.5B model needed about 520 training steps and roughly 1,900 H800 GPU hours. Compare that to, say, Nematron 1.5B that took 2,500 steps, used 8 different training stages, and needed around 16,000 H100 GPU hours.
16,000 compared to under 2,000. That's a huge difference in computational cost. A massive efficiency gain.
It really is. It suggests this approach isn't just effective, but potentially much more practical to implement. The paper also digs deeper into why these constraints work so well. They did ablation studies, testing what happens if you change things. For the KL regularization, they found that having none at all was bad. The model's output quality dropped quickly, lots of repetition. That's model collapse. But making the KL penalty too strong, like a weight of 5005, also hurt performance because it just slowed down learning too much. So finding that right balance was crucial. And with the clipping constraint, changing the range for the low-entropy knowledge tokens had a big impact. Make it too wide, and the model might start overfitting, just memorizing training examples. Interestingly, the model wasn't as sensitive to the clip range for the high-entropy reasoning tokens. A wider range there seemed to mainly encourage more exploration later in training, which is probably good.
So it really confirms that careful tuning for each token type is key. Keep the facts solid, let the reasoning explore, but not too wildly.
Right, and they even have these diagrams in the paper showing the PPO clip regions. You can sort of visualize how Archer expands the optimization area, the learning zone, specifically for those high-entropy reasoning tokens. It means the model gets clearer feedback, stronger rewards or penalties for those crucial reasoning steps, depending on whether they led to a good or bad outcome.
It sounds like it's really channeling the learning effort where it counts most for improving reasoning. That makes a lot of sense.
Yeah.
And you mentioned something earlier, a cross-domain benefit. That sounds surprising.
Yes, this was another fascinating finding. They discovered that training the model with RLVR on, say, math problems actually led to noticeable improvements on coding tasks. And the reverse was also true training on code-improved math performance.
Okay, that is unexpected. How does practicing math make an AI better at writing Python code, or vice versa?
Well, the analysis suggests it's not because the model learned new math facts while training on code, or vice versa. It wasn't about specific knowledge transfer. It also didn't seem tied to specific types of problems, like algebra versus geometry. Instead, the improvement correlated more strongly with the intrinsic difficulty of the problems. Tasks where the original base model was already somewhat competent saw the biggest boost from RL training, no matter the domain.
So it's less about the topic and more about the underlying thinking skills.
That seems to be the interpretation. The researchers argue the improvements came from enhanced general reasoning abilities, things like better structural organization, the answers had a clearer logical flow, more attention to detail, catching edge cases, and improved contextual consistency, being better at using information from earlier steps in the reasoning chain. This really reinforces their main idea. RL seems to primarily help LLMs by improving how they organize and apply the knowledge and skills they already have, rather than just stuffing more facts in.
So, bringing this all together for you, our listener, this deep dive into Archer really shows how these sometimes subtle-seeming adjustments in AI training can lead to pretty major gains. By recognizing that different parts of an LLM's thought process, represented by tokens, have different jobs, researchers found a much more efficient way to teach them to reason effectively. It's not just about memory anymore.
Exactly. It points towards a future where LLM improvements come increasingly from these smarter, more fine-grained optimization techniques that respect how language and reasoning actually work. It's about nurturing the model's ability to think logically step by step.
It's a great example of how tailoring the learning process can unlock performance. Makes you wonder, doesn't it? Where else could applying different constraints to different parts of a complex system lead to similar breakthroughs? Something to think about. Thanks for joining us on this deep dive.